Alright, so I'm Nicholas Carazo, the leader for the bomb powder experiment our group's going to do next week. Part of our group is Anthony Genova, cameraman, Vice Radley, and Richard Carazo. So a little bit of introduction is we're designed to measure the heat released by combustion of the solid and liquid samples in the oxygen bomb. And the reason we do this is because the calorimeter still to this day has been a good measure for to actually measure the heat of combustion. And the objective is to become familiar because it's so handy still to this day. You want to learn the background and fundamentals of how to do it. And also to measure both the thermal capacitance of the calorimeter along with the gross heat combustion. So in theory, upon igniting the bomb, heat is going to be transferred from the internal bomb surface to the surrounding water environment by conduction. And by observing this rise in water temperature along with some thermodynamic, the first law, can determine the amount of heat released by the combustion. So this is the equation. This is to calculate the thermal capacitance of the calorimeter. We need the internal heat of combustion along with the delta, the change of temperature, which we will do next week for fun. We can do this by trial. And the cool thing about this is once you find the thermal capacitance of this equation, you can use that as long as you assume always constant volume. So as long as the thermal capacitance doesn't change, you can find any measure as long as you have delta T along. Once you have delta T and the thermal capacitance won't change, you can find the heat of combustion for anything. And so for the equipment in the left hand, it's kind of the big picture items. And as you can see, steps 1, 3, and 4 of the apparatus is not shown because it's not part. It's like extra. Kind of it's the igniter, the laptop, and the analog to digital converter. And what is shown on the left is the stainless steel bomb and the water bucket that we're going to be using, the thermocouple, and the water stir. And then the right is actually a better picture of the bomb, kind of in a expanded view. And it shows all this, the bomb lid, all the fundamentals of the bomb that we'll be using to get familiar with. And so as far as the setup, as far as for the setup, it's kind of broken into 3 sub-assemblies. First one, bomb preparation. Measure and cut 10 centimeters of Ni chrome. Place the known fuel sample in the crucible. And they say if you're unfamiliar of what the specimen you're testing, don't go over a gram because it can actually blow up the bomb and damage it. And connect the wire with the electrodes. Add 1 milliliter of water, distilled water, that's pretty important. And make sure you don't get any water in the crucible itself. And close the lid and alternate it until you reach 30 atmosphere of the bomb pressure. And for the water jacket preparation, you add 2 kilograms room temperature water and put that in the calorimeter jacket. And for the instrumentation, you start the computer and go to the website listed below and plug in the thermocouple into the slot, place the thermocouple in position, and start get familiar with the data acquisition system. And as far as this, that's the sub-assembly. So as far as the big picture, carefully lower the bomb to the bucket, connect the electrical leads to the bomb terminals. We're going to check the ignition circuit, make sure it reads 0 to make sure the equipment's right, and make sure all the equipment, the stir and the thermocouple are submerged and out of contact with the bomb or bucket before you start, and turn on everything and try it out. As far as the experiment, we're going to start by recording the room temperature data for about 2 minutes, and then we're going to ignite it and continue to take the data for 2 minutes. And once it reaches about, I don't know, I'm not too familiar how long it's going to take, but once it reaches room temperature, you're going to stop logging the data and save it. And then once you have that you can replace it with any unknown fuel and find the combustion. And as far as shutting down, turn off the stir, as Sean said, remove the lid, disconnect the bomb, depressurize it, and just clean up after yourself. So expect the results, and the manual is said to use 2 kilograms of water, 3 kilograms of stainless steel, specific heat. I use the mean also 510, 42, 4,200. And for the C total, you kind of break it into mass specific, and you multiply it by each, and you get 9.9 kilojoules per kilogram. And then for the benzoic acid, we use the C total, which we found up here, and we're using 1 gram, and the enthalpy of combustion is 3232. And so you can multiply by mass times the total of C, divide that by the enthalpy of combustion for the benzoic acid, and you get 3.07, which is pretty close to what the other groups got last week, or 2 weeks ago. And the sources of error, beginning with the human error, the ignition wasn't cut, the fill line wasn't to exactly 2 kilograms of water. Water gets to crucible, which would be catastrophic, and the water is plus or minus 5% of the room temperature, and the wire and fuel are not, you're supposed to place them in kind of slow and make sure that, you know, you don't kind of stir them up. And as far as the computer, I can't really do control. Some tables, like the rounding errors, and the tables have variations of constant of what they, you know, their standards. And also the temperature probe that hits inside the glass would cause a large amount of error also. And practical uses, we can measure the heats of combustions of unknown fuel and how efficient those are. Any questions?